All right, guys, welcome back. Sorry for the delay again. Any questions we get before we get started? Everybody good with the project? No more questions? Cool. So for today's plan is I'm gonna just finish the last portion of what we discussed last lecture, and then we're gonna move on to the paper presentations. So starting last lecture, we kind of switch gear, and start thinking about one real system to kind of like, apply things that we learned so far. And we picked machine learning just because machine learning becomes more and more interesting problem, just so, very widely used, becoming more and more popular. And it's one of those things that potentially could change our lives and actually start beginning to make those changes, right? So we want to look at the machine learning as a system and then see what are the potential problems that we have. Before jumping into the machine learning part, the attack part and the security part, we had to go over fairly boring stuff that probably most of you already know about overfitting, about what is machine learning, different classifiers, and then we specifically zoomed in on neural networks because most of these attacks are actually focused on neural networks, mainly because neural networks is basically the most popular part of the machine learning and most I would say powerful part of the machine learning. Specifically, deep neural networks is what these days people are looking at. And usually these deep neural networks, the three different types, there's feed-forward networks, convolutional neural networks, and RNNs or recurrent neural networks. And you can actually also combine them together. So you can have a piece of, something like a convolutional neural net plus some feed-forward or fully connected, or there are actually some that has some recurrent combined with, for example, convolutional and so on. So that's kind of like was the summary of what we're looking at. Something like this that is very deep, many different layers, combination of multiple different layers. And in addition to neural network layers, you also have things like activation layers such as ReLU or tangent, hyperbolic, and so on and so forth. And then you also have things like pooling layers in order to reduce the dimensionality. Okay. So, and then this is like the state of the art for deep neural networks. Of course, it's much more wider than this. If you're interested, you probably have already taken more courses on this, or you will take more courses in future. But that's kind of like where we are in terms of neural networks and deep neural networks. So now it's actually we started focusing on the security part of this and how we actually want to attack this and what are the options for the attacker and what are the options for defending against these attackers. Before that, is there any question about things that we discussed so far?
I was a little bit confused about what the activation layer is.
The activation layer is basically, there are multiple. So first of all, the motivation for the activation layer is kind of like the way that the actual neurons in our brain works. So basically, neurons kind of like step kind of behavior they typically have. So there is some values that accumulated in the inputs, and usually if they pass some thresholds, the neuron becomes activated, so they send a pulse to the next neuron and so on. For artificial neural network, basically this is what we are looking at. The idea is that you have multiple neurons that are connected to one specific neuron, right? So basically, what you do is this the sigma of WIXIs, right? So these are XIs, and they all have some weights, right? So what you get here at this point is WXI. We also said that usually you have some sort of a bias as well. And this is typically what you have here. the sum of all these results. Instead of sending this to the next stage, usually what we do is that we have some sort of activation function here. And there are multiple different options for the activation functions. The ones that's very popular just because of the simplicity is what's called a ReLU or rectified linear unit, which basically all it does, it has this transfer function like this, which all it does is it doesn't send anything that is below 0, and it just passes everything that is above 0. So basically, the mathematical function of this is max of x in 0. Okay, which means that if the number is negative, it's just going to pass 0, which is this range here. And if the number is above 0, it's just going to pass it the way it was. So basically, this is x equal to y. And this way, basically, this would be the input to this activation layer. So this would be the x in this particular function. And the output would be either 0 or would be x. Okay. And that would be what this activation layer does. Why it works is, again, is because basically the idea is mimicking the behavior of an actual neuron. And this way you can actually mimic that behavior. There's a completely different idea for neural networks, and that's what's called spiking neural networks. So this is more of like, an actual, continuous number. But there's another class of neural networks that are actually getting more and more interesting these days, and that's spiking, where this can be completely different types of computation, which is basically sending some spikes. And there are lots of challenges in terms of building the actual hardware to be able to send the spikes, but yeah, it's nothing to worry about, but just have an idea that that's also another possibility. Does that make sense? Okay. So now that we kind of know what we're looking at, and generally it doesn't have to be deep neural nets. It could be any machine learning algorithm, but let's focus on deep neural nets for now. So what is important for the adversary? And basically, there are two things that the adversary wants to target. One is fooling the system in some sense. And basically, the goal here is forcing the system to make a wrong decision, because we said that we're basically looking at a classification problem. And the classification problem at the end of the day is outputting some label, right? And all the attacker wants to do is forcing that system to make a wrong classification, decision, right? And we kind of already gave you some different examples of how this could be useful. This could be useful, for example, in an autonomous car, in malware detection scenario, and so on and so forth, right? The second thing is basically stealing information from the system, right? Same old thing that we kind of already discussed multiple times. In here, what is important is either the input data or the weights. And we basically say that these are two class of problems that we need to worry about machine learning. We typically, call this, the first one in this class, security problems, and the second one, privacy. And we start focusing on the security problem. I'm going to finish that in this lecture. On Wednesday, we're going to start, on Thursday, we're going to start talking about the privacy aspects of things, all right? And this is kind of like summarize the system as a whole. Remember, I said that basically systems as a combination of sensors, local processing, actuator, network, backend processing, and so on. For machine learning, I gave you two examples. One is an automotive computer vision system, which basically think about it as a Tesla, which has multiple different cameras and tries to use those cameras to do the autonomous driving. The second option is basically these malware detectors that we extensively talked about. Think about all those papers that we discussed last week. In both cases, you have some sort of interaction with the physical domain. That could be traffic sign, that could be the network traffic. And then we step by step go through different steps of the system. I already described this, so I'm not going to go and re-describe it. But eventually, what will happen is that you're going to have some inputs to your system, to your machine learning system, And all you can do is basically change things here. We are assuming that the system itself is functioning correctly. So there is no like buffer overflow or anything happens inside here. We basically, as an attacker, we can change things in this domain here. We can change things in the physical domain. We can change things in the digital representation. Eventually, we send what's called an adversarial input to the system. And hopefully this adversarial input is designed correctly so that once we actually do this output is an incorrect output, right? And when this is an incorrect output, the action that caused by this output will create some harm, will create something that is adversarial, right? So that's the goal of the attack. Any question here? Is it obvious? Cool. So what can the attacker modify based off this picture? There are two things that the attacker can do. Basically, just going back to the way that the machine learning system works, specifically deep neural nets. If you remember, we said that generally there are two phases for designing a machine learning system. There is a training phase, and there is a inference or testing phase. Right? So in order to attack this system, obviously the attacker also has options to attack at this point, this way, or attacking at this point. The first class of attacks that tries to impact the system during training, usually called poisoning attacks. The idea is that when we are training the system, obviously we have lots of data sets, labels, and records. What the attacker would do is extend this data set with some adversarial samples or poison data, and these are input data sets that are incorrectly labeled, right? And it's intelligently and smartly incorrectly labeled. This is not just any inputs that we label it incorrectly. We label it incorrectly with specific algorithm or system. And basically, our training set would be this instead of only this. An alternative scenario would be that changing these labels here, basically, so we don't extend the input data set, we just change the input data set. And what would happen is that if we design these adversarial inputs or poison inputs correctly, when we are training our system, basically our machine learning will be trained incorrectly. And as a result, when during the inference, we send a label that is one of these classes, it's going to be labeled incorrectly. And that's exactly what we want, right? So we want to fool the system and force the system to make a wrong decision. So that's kind of like, the trick that, and the adversary can use in order to force the system to make an incorrect decision, okay? I gave you one example of a spam email, and basically the main thing to take away from this is that basically the attacker, all it does is moving the decision boundaries. So it's such that the next time the adversarial inputs comes in, because we force the system to make an incorrect decision, then we can actually, and during the attack time, we can actually, pass the detection algorithm or whatever is being used for the machine learning. That was the poisoning attacks. There were different types. Usually, targeted poisoning is basically a specialized version of the poisoning attacks, where the idea is not only just force the system to make a wrong decision, but also force it to make a specific decision, right? So this is actually like more sophisticated attack, because we not only want to make sure that the system is making a wrong decision, we want to make sure that it's actually the decision that it makes is exactly what we want. So we kind of like, it requires a little bit more work, but it's much more powerful. And then the third class was what we call backdoor poisoning, which the idea was we kind of like, add specific features to the system, train it to see whenever they see those features, they make a particular decision. And during the attack time, what we do is that we add those features to any image that we want or any input that we want. And the system, since it has learned to associate those features to a specific class, they're always going to decide and classify that specific class. So it's kind of like, we have this label or we have this patch that if we apply to any input record that we have, we are kind of guaranteed that it's going to like, be the class that we want. There are also lots of challenges, and when you actually read these papers this week, you will see the challenges in real world setups and how people actually come up with newer ideas and more sophisticated stuff. So most of your paper readings would be about real world challenges and in real world, how do we implement this? Okay. So now let's focus on the second thing, which is attacking during inference time, which we usually call it evasion attacks. We evade the system from making a correct decision. Any questions so far about poisoning? So I gave you some examples. So the difference between evasion.
What's the backdoor poisoning?
So backdoor poisoning means that when we are training the system, we are adding specific features, and for all the poison samples, we always add those features, and then we always label them usually one thing or at least a class of labels. And what we do during the inference is that since the system has learned and associated those features to those classes and those images, whatever image that we have or whatever record that we have during the inference, if we add those features, it will automatically label the input to that class. So for example, to give you an example, typically what people do is, let's say you have an image of a scenery or whatever. For example, the backdoor would be something like, I add rectangles into the two top left and bottom left corner of the image, okay? And whenever I add these two, small rectangle, I'll always label this as something like a ship or whatever class that you want, okay? So even though that this could be any other, image, I always, force the system during the training to think that this is the ship. And what will happen is that people have found out that if you do this, basically what the machine will learn is whenever they see these features, they think that this is a ship. So basically ignores the rest of the image mostly and always associate these rectangles with ship. So what we do during the inference is that now we have another record that has something else. Let's say it's a horse, it's a car, whatever. All I need to do is just adding these two small rectangles here. And kind of like I have a backdoor to the system, right? So whenever I want to enter the system, I can always add those patches and then enter the system. Any other questions? Okay, so during the evasion, what we do is that we don't change anything during the training. So the system is as is, it's normally been trained. Nothing happens during the training. What happens is the attack actually completely happens during the inference. And all we do is that we take the original image, whatever, the original sample, whatever that is, we added, we modified with some strategy that we're going to discuss, and then we create this new sample called an adversarial sample, and then if we pass this to our machine learning system, what will happen is that we will see that it's going to be an incorrect label. Okay. For example, in this particular example, which by the way is taken from a real attack, obviously this is a dog and should be labeled as dog, so this is correct. During the attack, what we do is we add this image with this kind of random looking noise, white noise, very weak as well, and then create this adversarial sample that if you look at it and compare it with this, you don't visually notice the difference. But when you feed this to the machine learning system, it's a deep neural network, it's going to label it as horse, okay? And that's how an adversarial attack would work. Another example is a voice record, is a voice signal, which originally should say, for example, how are you? What we do again, we modify it and add some adversarial noise or perturbation. And what will happen is that again, if you just examine this and compare these two, at least visually doesn't seem to be a significant difference between them. But when we feed this to the machine learning system, again, we're going to get an incorrect label, which in this case is, for example, open. Okay, that's the idea of evasion attacks. So these are usually what's called digital evasion attacks, because what we do is we are changing the digital representation. Okay, but an alternative to that is physical attacks, where we actually change the physical domain, and that eventually results in an incorrect label decision. So, for example, if you have a normal stop sign, and if somebody actually go and physically add, a patch to this stop sign, so on specific street they go and add this patch to this stop sign, and then, for example, the autonomous cars such as Tesla or whatever use their cameras to read this stop sign. People have shown that this is actually indeed results in a different classification label. Depending on which patch you're actually adding, this could actually result in different labels as well. So one could be yield, one could be speed limit, could be many other things as well. All right. So if I go back a little bit, so as I said, basically the attacker can change this part. The first class of examples that I show you is basically changing the digital representation, right? So for example, we have a duck image and we added the white noise to it. We basically change the pixels. So we change this part here or this part here. And the second attack that I show you is usually called physical attacks, which basically what we do is literally changing the physical domain. And when the sensor reads this information, it makes an incorrect decision. Okay, so these are the two classes of attacks that can happen during the event. Any questions? So yeah, this is basically what I just said, that there's two classes of evasion attacks, physical and digital. Physical, so the difference is, obviously physical is slightly easier to do, because all you need to do is actually changing the physical domain. You don't need to enter the system and change the digital values. But on the other hand, physicals are typically easier to detect because you need to actually visually, for example, if it's a vision problem, you need to change things visually, which usually it's easier to be detected. So for example, obviously, someone can, examine this and say, oh, there's a small patch added to the stop sign. But there is actually attacks that tries to make this a little bit more invisible as well. So it's not like, very simple that people can easily say, oh, there is an attack. But this still is slightly easier to be distinguished from a normal attack. So questions here.
Yeah, I mean, you might go over this a bit, I'm not sure, but with modifying an image, is that something that, would the attacker have like a model, like a replica of the model on their own, and so they experiment to determine, oh, modifying it this way, or can you use an algorithm for that?
Yeah, we're actually gonna, like in the next 2 slides, we're gonna go through how we actually do that process, but it's exactly right. So what you do is kind of like an iterative process. You either use a shadow model, which we usually call it, like a replica of the model, or you can even query the actual model.
So does that mean that the attacker can only access, or you can only attack models that are predictable?
All the models are always predictable, right? Like these, for example, let's say you buy a Tesla and there is a autonomous system with it, right? You can always play with that and see what's the decision. And the idea is that all the Teslas would probably have the exact same behavior, right? Because it's at the end of the day, this is a piece of software anyway, right? So the same software in multiple different instances will have the same behavior.
With a physical attack, there's also a possibility that it's not always like intentional, right? With this case, I guess it depends on the model, but it could just be the case where like a white paper is blown by like a white.
Yeah. So I mean, there is a whole bunch of, and machine learning domain, there is a whole bunch of robustness issues. And the robustness issues are when the nobody's actively trying to make an error to the system. So basically, the the nature is the source of randomness or source of unpredictiveness or source of faults. And you obviously need to design your system to be robust against all of those, right? So for example, if it's raining, then your system should still work. If it's cloudy, your system should work, right? So you need to be, when you're designing your, for example, your vision or whatever, your voice recognition and all those things, you have to be very, very careful about the robustness aspects of the things. And that's very important. What we're looking at here is actually a slightly more difficult problem, because then the adversary also tries to create some errors, but these errors are slightly more intelligent than the errors that are created by the nature, right? So it specifically tries to be stealthy, for example, or try to be smaller, so much more difficult to detect and so on and so forth. So, but usually, robustness and adversary is very relevant in some sense, because both of them are kind of injecting some faults or some unexpected behavior to the system, and hopefully our system is able to detect both of them. Does that make sense? Okay. So this is the difference between physical and digital. So how do we actually launch a digital attack? So obviously we need to somehow infiltrate the system using the sensors and all those tricks that we discussed previously, that you can launch a malware and so on and so forth, can kind of be applied here in order to change things in the digital world. Okay. So to kind of understand both poisoning and evasion attacks a little bit better, it's also useful to go through the assumptions and the threat model of these systems. So generally, if you think about how to launch these attacks, the first things that we need to answer is what sort of information or knowledge the attacker has. And the four main things that we need to always pay attention to is whether the attacker has access to the model. And when we are saying access to the model, it means usually exactly know what the structure of the model is, right? Because let's say, for example, you want to attack a voice recognition system, something like Amazon Alexa, right? You necessarily don't know exactly what is the internal of that system is, particularly, for example, is it a CNN? How many layers it has, what is the size of each layer, and so on and so forth. All right. So finding the structure of the network is actually an important knowledge that the attacker needs to know sometimes and may not need to know. And this is usually then depending on how much information the attacker has, there could be different class of attacks the attacker can launch. We usually call it white box, black box, and gray box. The difference between them is that the white box is basically when the attacker knows everything about the model, structure, the size, etc., etc. Black box is exactly the opposite. The attacker has knows nothing about the system. The only thing that the attacker can see is the inputs and obviously the outputs. Anything inside this is a black box. And gray box is kind of like somewhere in between, where you know some information about the system, but you don't know fully what's going on, okay? And depending on this, as you will read some papers, you will see that, whether you have a black box access, whether you have a white box access, or whether you have a gray box access, your attacks and your strategy needs to be different, okay? And if you think about this, is actually kind of goes back to obscurity and security thing. So black box is kind of making the system obscure, right? So what you want to have ideally is, if you want to follow the security principles, you want to be able to have a defense mechanism that even with white box access to the system, the attacker still cannot, successfully attack your system, okay? Because if you assume that this is a black box system and the attack is unsuccessful, you always have to be worried about what would happen if the attacker gets that knowledge and now attacking your system as a white box, and what would happen, right? But if your defense mechanism is actually works with white box, then you are guaranteed that this system also works for black box, okay? So ideal defense mechanism has to kind of like follow this to actually basically follow the security by obscurity kind of challenge that we always discuss. Does that make sense? Any questions here? Cool. So that's number one. The second thing that the attacker may or may not have access to is access to the data set. The data set that used for training the system. The access to the data sets has two main things that we need to be worried about. One is that when we're saying access to the data set means that whether the attacker can actually change the records and labels in that data set, so that actually would be applied to something like poisoning attacks. The second thing is accessing to data set means that the adversary can train some sort of a replica of the model, right? So if we know, for example, the structure of the system, and if we know that what is the data set, basically we can use this to start the training ourselves. So we can train the system using this. And what we're gonna get is a replica of the model, right? So the original model used the exact same behavior that what we did, right? So they also take the structure, take the data set, train their system. As an adversary, what we can do also is, if we know the structure, if we also have access to the data set, we can basically create a replica of model. You're gonna read some papers that what is this replica and whether you can actually achieve 100% accuracy with this. But generally, the idea is training is some sort of deterministic. It's not exactly deterministic because you use some stochastic gradient descent, but typically you can get very, very close to the original system, okay? So accessing to the data set means that the adversary has much, much more power, much more degree of freedom to launch a successful attack, okay? The third thing to pay attention to is whether the adversary can actually query the model or not. And when we're saying query the model, basically what the attacker can do is that instead of creating a replica, so let's say this is the original system that we want to attack, what the attacker can do is creating this replica of the model, right? And basically query this in order to create the adversarial sample. Alternatively, what the attacker can do is that just get rid of this replica and then just play with the original model and query the model, multiple times. So for example, let's say you want to see whether your Tesla, so you have your stop sign, right? And you want to create this patch here to fool the camera of your system, right? So, and then let's say you have actually access to this model because let's say you buy a Tesla and then you can actually play with it. So all you need to do is start, iteratively playing with this machine, right? So you add a patch, you see what is the output label of this machine learning algorithm is, and then you change your patch again. You wait for the system to respond, and then iteratively you do this over and over and over again until you actually find the patch that you want. And this way you can actually create your adversarial sample, right? So if you actually can query this model infinitely without any limitation, the power that the attacker is gonna get is much more significant. And now compare this to the scenario of which that you cannot query the model, or you can only query the model with limited amount of time, like maybe 100 times or 1,000 times or so, right? In that case, your iterative process is very, very limited because you can no longer, just keep changing things and query the model, keep changing it, query. You have maybe only 1,000 times or 1,000 tries to actually find. So the algorithm or the strategy that you need to come up with in order to build your adversarial samples would be significantly different, okay? And there are lots of, actual real systems that this is actually indeed a problem. Like if you, for example, the querying the system is a paying system, for example, something like AWS, that anytime that you send something, you need to pay, then of course the querying would be something of a limitation, right? Or these days there is kind of anomaly detection methods that tries to detect these kind of attacks. That if somebody is sending lots of queries, it potentially means that this is a potential malicious user, right? So querying the system is something that we need to decide when we are designing our attack. And the last thing is basically just backing to the various types of attacks is whether we have physical access to the system, whether we have digital access to the system, whether we have both of these, none of these, what we have, right? What can we change in the systems? Of course, if you have digital access, that is more powerful, but sometimes we only have, for example, physical access. So we need to come up with physical changes in the environment in order to attack the system. Okay, any question here? Okay. So it's just kind of like, just going back to what I said here. So physical versus digital, white box versus black box versus gray box, one time versus iterative, which basically means that how many times can we query this model? Sometimes we only can query this model once or more, or limited amount of time. Sometimes we can query this model iteratively for infinite amount of time, and that's what we have. Okay. Another thing to also pay attention to is that in evasion you have basically two options, right? You either wants to just fool the system and make the system to make an incorrect decision. And in that case, we basically usually call it untargeted attacks or generic evasion attacks. But sometimes you actually wants to be even more sophisticated and have what's called a targeted evasion. So you not only wants to say that, oh, this is not a stop sign, right? So that's basically the scenario number one. But you also want to say that this is, for example, a speed limits, traffic sign. So by adding this patch, not only I want to make sure that the system does not recognize this as a stop sign, but it also wants to make sure that this is actually being recognized by speed limit. And that's a much more sophisticated and obviously much more complex attack to do. But interestingly, people have shown that this also can be achieved. Okay. And again, you can think about lots of scenarios where this might be something that people do want, right? Where you have multiple classes, but you specifically want this class to be used. Okay. Any questions here? So this is basically what I just said, targeted versus untargeted. And this is kind of like, just a generic idea of the attacks, physical versus digital, white box versus black box versus gray box, one time versus iterative, and targeted versus untargeted. So you can have a combination of all of these. So you can have a physical, white box, iterative, untargeted attack, for example. You can have a gray box, physical, iterative, untargeted attacks, and so on and so forth. But there's a huge, types of different, groups of attacks that the adversary can do. And basically, you'll need to know what is your, threat model and what exactly are you trying to protect from, right? And on the adversary side, the adversary needs to know what are the capabilities of the adversary, and then based off that, design their attacks, okay? Whether I have access to physical domain or digital domain or both, whether I have knowledge about the structure, whether I can iteratively query the model, whether I want targeted or untargeted, and so on and so forth. Yeah, so I mean, at the end of the day, you want to attack a machine learning system, right? And machine learning itself is, if you recall, we usually talk about, deep neural networks. So deep neural networks has multiple layers. Some of them are CNN, some of them are max pooling layers, some of them are ReLUs, etc., etc. The size is different, right? So all those things, right? So that structure actually plays an important role of your success rate and how you actually create your adversarial sample. And in order to create your adversarial sample, you basically have 2 or 3 options. One is you either know exactly how this look like, what this structure is, right? And we call that white box. You basically know exactly what's going on inside. Think about it as like, an encryption mechanism that you know exactly what the algorithm is versus you don't know exactly what the algorithm is. So white box is when you know fully what the algorithm is.
Black box when you only know partial.
What's that?
And then black box you only know partial.
No, black box means you know nothing. You just know the inputs and you see the outputs. You don't know what's going inside.
Oh, okay.
So it's completely black.
Okay, okay.
And the gray box is somewhere in between. And as I said, going back to our discussion on security by obscurity and talking about, the Shannon theorem that, your encryption system should be completely transparent. On your machine learning system, you also want to have to be capable of defending against white boxes as well. Of course, there are some scenarios that you can show that your system is black box and show that there's other ways of making sure that it stays black box. But typically, when you're coming up with defense, you should assume that the attacker has full knowledge of your model and structure and everything, and you still are capable of defending against that. Okay.
So, I guess a general question, with all the papers we've been reading, a lot of them focus on propositions of attacks, but they don't really go into the detail on how to prevent those attacks. So whose responsibility is it, and who does the bulk of the work of figuring out the defenses?
So when you're let me see if I understand the correct question correct. So when you're coming up with a defense, you have to clearly state your assumptions. So what are you exactly defending against? Okay. So for example, you say that, oh, I have this idea for defending against attacks, but the attacks that I'm defending against is, for example, gray box attacks that are untargeted, et cetera, right? And this is basically, then it's down to the actual user who wants to implement this defense to decide whether this is a useful defense mechanism for them or not, right? So for example, ideally as a company who probably employs this, they have to think that, okay, is this a realistic attack surface for us or not? And to have a full end-to-end defense mechanism, you have to say that, oh, okay, if our assumption is that this is a gray box attack, we need to make sure that this stays gray box, right? So these assumptions are not violated. So it's kind of like two things, right? So one is coming up with the solution and state what your assumptions are. And then when you're actually using this specific solution, you have to make sure that those assumptions stays correct, right? So that's usually how it works. Okay, so obviously, given that there is this different options, the challenges also is unavailability and difficulty of achieving this. For example, the complexity of the networks plays an important role. The number of queries that we need to use in order to attack the system is important. What is the output of the system is also very important. Something to pay attention to is that typically two types of outputs one machine learning system can generate. One is just usually giving you the final label, saying that this is the label that the system decides. Other systems, since this is machine learning is a multi-class classification problem, right? So at least you have two different classes and you want to decide between the two. So another option is that the machine learning system is actually giving you the confidence value of all the classes, okay? So basically saying that, oh, there's 90% chance of this is class 1, maybe 0.0% chance is class 2, maybe 0.05 class 3, and so on and so on. So give you the actual numbers, the actual confidence values for each of these classes. And if the system provides this, the confidence values, it makes the life of the attacker much more easier because there's much more information to play with for the attacker. But on the other hand, it's also very convenient for normal users if he gets this confidence value. So again, there is a problem between convenience versus security that plays a major role here. Okay. And then the final thing before jumping to the paper presentation is, okay, now we know how to attack the systems and what are the different options, what are the challenges and so on. How do we actually create those adversarial samples? So the very first thing is that, as I said, we need to first find those assumptions and know what those assumptions are. What are the goals? What is the attack type and all those things. So once we have all of that, then we can actually build an algorithm that actually creates the the adversarial sample. The way that we create the adversarial sample actually is very similar to the way that we train machine learning system itself. So remember, what we do when we are training the machine learning system is that we have lots of records of X and Y's, right? And we pick a structure and we basically, send this, we get the loss, right? We back propagate the loss, and then we do that iteratively until we minimize the loss. Remember, we talked about gradient descent and finding this minimum point that your loss is minimum, right? So finding the adversarial sample is kind of very similar practice to that. So what you want to do is that you want to train, you want to create an X such that, f of X is equal to Y. And this Y that you want to create is basically the adversarial label that you want. So for example, if the original X, so let's call it Y prime, if the original X results into Y, which is the correct label, what you want to do is substituting this Y to this Y prime, which is an incorrect label, right? And how do we actually create that? It's an iterative process. So you start with X, right? And you start adding some sort of a noise to it. And you gradually change this noise until you find a point at which that this Y flips to Y prime. And that's where you have your adversarial sample. Remember that we always said that basically we have X and Y, and our adversarial sample is usually X plus some small noise that results into a Y prime where Y prime is not equal to Y, right? So that's exactly how we create this. And we can create this during the poisoning attacks. We can create this during the evasion attacks. We can create this for targeted. We can create this for untargeted, and so on and so forth, right? So for example, if it's in targeted attacks, the satisfaction requirement is not Y is not equal to Y prime. You actually want Y to be exactly equal to a specific class that you want, class C, J, or whatever you want to call it, right? So you keep changing your X until you find that small perturbation, small noise that results into that specific class, okay? So you need to iteratively do that until you reach to that, okay? So that's typically the idea, yeah.
So with something like gradient descent, we're essentially taking an input, or like taking a result and looking at its error and sort of trying to minimize that error iteratively, right? Like we're moving down by like calculating the gradient and whatnot. So is this process like a reverse gradient descent where you try to like maximize the error until you end up flipping the output to something that
you can call it that way, but still you're minimizing the error, but your error is the difference between your output and the targeted class that you want to achieve, right? So in normal gradient descent, you do X and then you get Y, and you want to minimize this loss. For adversarial sample from X, you want to get to Y prime, and you're trying to minimize that, right? So in both cases, you're kind of minimizing the loss. The difference is that in normal training scenario, you're trying to get to the actual correct label. In adversarial training, you're trying to get to an incorrect label. But yeah, in other words, if you compare these two, you're trying to maximize your loss your normal loss as much as possible in some sense, yes. Okay, so very quickly, let's go through, let me use the defenses maybe in the next class. I don't want to take too much time because on Wednesday, I'm going to talk about the privacy aspects of things as well. So I'm going to just keep this for next lecture. All right, let's have a 2-minute break and then start with the paper presentations. Okay, so let's get started. We're a little bit behind, so hopefully we can actually make it in time. Yeah, go ahead, guys.
Can we start?
Yeah, please.
Okay, hi everybody, I'm Abhishek,
I'm Sahil.
and our paper is return to libc without function calls. So basically this paper is about how you can do a return to oriented programming using buffer overflow, but it does not particularly talk about how you can get it in the system, but rather about what you can inject after you get into the system.
Okay, so before we get started, just to show of hands, how many of you guys remember what you did in Attack Lab in CF33? Okay, good. Okay, all right. So just to get started, we're gonna talk about what exactly we can do to inject code, and there's three specific things. Buffer overflow. I'm assuming most of you know this because we've also discussed this in this class. So it's basic. I'm not gonna go over the details of it. Integer overflow or underflow. The basic idea is that if you have like if your input is expecting a signed number and you input something like -1, which is all ones, and it gets interpreted as unsigned, it basically is the largest possible number, and then that can corrupt like the stack that you're pushing that input value into. And then the third thing is format string vulnerability, and then that's basically like a buffer overflow, but with a string instead of injecting a number, wherein the string you like give as an input, you can like have it execute some command and thereby gain control of the system that compromises security. So this is step 4. The return-oriented programming is a step forward from the buffer overflow attack. And here's basically what it can do and what it cannot do. So given the possibility of buffer overflow attacks, the solution to address that was ASLR and creating a non-executable stack. But with return-oriented programming, you have gadget forms. So you can basically create using the binary code for any program that you have. You just use that and call functions that you want in a way that it circumvents this ASLR, and also allow, even if the stack is not executable, you can call the function that you want. But the thing it cannot overcome is the stack smashing protection, because so stack smashing protection, null byte issues, and 100% arbitrary code execution. So stack smashing is when the basically it's like the stack has a stack protector, and if that gets overwritten or corrupted, the stack knows that there is an adversary who's trying to attack it. Null byte is when if you're reading the input to your system as a C string, null byte is the terminating byte. So if you have that at the start, then your system won't read anything past the null byte. And then 100% arbitrary code execution. This is where the return into libc comes into play, where your return-oriented programming cannot help you solve this issue, but if you have return into libc, you can. And 100% arbitrary code execution means you can, since libc is like the standard GNU C library, you can use that and any of the functions in that available to you in order to like call or get any kind of behavior that you want as an attacker. All right, so again, this goes into returning to libc. Basically, it allows the attackers to be use the x86 executable, and the widely used WX or defense technique eliminates the possibility of code injection attacks, but allows for returning to libc attacks. So WX or X means when you have write permissions, you don't have execute permissions, and when you have execute permissions, you don't have write permissions. You can only have one or the other. You can't have both at the same time, and that helps you prevent against code injection, but not the return into libc. And this means that we can utilize existing code in libc standard library to run any code of our choice in order to generate an attack. All right, so standard C library contains almost every Unix program, and mostly the system calls and the wrappers are the most useful ones that the attackers use to generate create these attacks. And since this makes the libc GNU libc library standard target for attackers. Basic this like the basic bottom line of any return to libc attack is that the only thing you need in order to create a successful attack sequence is a return instruction. Like as long as you have the return instruction at the end, you can inject or create a set of codes using gadget forms in whichever way you want before that. And then as long as you have an RET at the end, you can execute that attack. Okay, just a couple of points on why return into libc is sometimes more limited than code injection. One is that you can only call one function at a time and one function after another. So you only get the capability of straight line code execution as compared to the arbitrary behavior that you can get from code injection, because in code injection you can use any kind of branch instructions to jump from one place to another. And that capability is you don't have it in return to libc. And the attacker can only invoke functions available in the text segment and loaded libraries. So if you remove those functions as in order to prevent against these attacks, then you can probably restrict some of the attacker's capabilities. All right, so how this paper changes the game. This is basically the Galileo algorithm is what this paper goes into. And this is an example of like why we use the Galileo algorithm. So if you look at this attack sequence of instructions on the top, if you get rid of the F7 over there and start reading only one byte later from the C7, you get a totally different set of instructions. And this is why we use the Galileo algorithm, in order to basically come up with useful attack sequences. And then the next slide we have here is just the procedure for the Galileo algorithm. It's pretty complicated. The only gist of it that you need to understand is that you basically create a tree-like structure, and the base or the root node of the tree is the return instruction. And then from that, like as the tree grows on from the return instruction, you go on looking for up to the point where you find a valid starting point for the instruction. So you start from RET, and then the tree grows downwards where you come at the end, the leaf node of the tree, you get the starting point of the useful instruction.
All right, so one of the biggest contributions of this is that it is Turing complete. Do you guys know what Turing complete is? Okay, just for those who don't know, it means that you can do whatever C or Python program can. That's pretty powerful, right? So what makes an attack Turing complete, or a sequence of instructions Turing complete? You have 3 requirements. 1, you can read from anywhere you want. 2, you can write to anywhere you want. And 3, you can make a decision based on a condition. If these 3 conditions are satisfied, you have a Turing complete attack. So you first you analyze the code using the Galileo algorithm, you combine the gadgets together to form your attack, and then you just pawn the system, you win. Let's get into constructing each gadget. First, we want to load a constant. How do we do that? The pop instruction, so this is the stack pointer. You pop the instruction, pop this constant, it goes to this register. So now you have the value in your register. You can use the other gadgets to utilize this value that is now in your register. It ends with a return instruction. The main reason why we wanted to return with, to end with a return instruction is so that we go back to the stack, which is where our instructions essentially lie, because for us, the executable is exactly the stack. We don't have the program memory to execute. We have the stack as our execute. But of course, stack doesn't allow the execute permission, so it points to different instructions. So now we want to load a constant from memory. How do we do that? We don't have a move instruction, so we can't exactly move whatever we want, but we do have a move with a displacement. So if we can load a value into EAX register over here, at a displacement of 64, we can load whatever value that this value over here plus 64 in memory points to, and that will go to EAX. How do we get any value to EAX? Well, we have the pop instruction. So we can load whatever value we want into EAX. Storing into memory, we have this gadget and this gadget. So basically it's the opposite of the previous one. We can move whatever we want from EAX into memory over here. And then we can, so obviously we can pop this value like a constant to or this register. We need a displacement of 24 because of course we don't have a straightforward instruction. We do have a gadget for this though. And then we can move the value whatever we want from EAX, and we know how to do that. Addition. This is a little complicated because we have a push over here. I mean, obviously we can construct these gadgets over here so that we can load the values that we want to add together. But the problem is this push instruction. What this does is that push lowers the value in EDI to the stack, so your stack pointer increments by 1. But when you return, now you have a different value because your stack pointer incremented by 1. So the way you can circumvent that issue is that if you have the next return address in EDI instead, your stack pointer goes down 1. Your next address would be over here, and then when return executes, your instruction pointer would go to whatever address over here would point to. So essentially, EDI would contain the return address. You have other arithmetic operations. Subtraction is nothing but but negated, and we have a negation gadget. Multiplication, well, that's addition multiple times. I wish we did have a multiple instruction, but we don't. Multiply instruction, but we don't. We have other Boolean operation gadgets, XOR and not or shift. One thing with XOR is that we have a push over here, but as we saw, we can circumvent that. Now an unconditional jump. So we've satisfied loading into memory, we've satisfied storing into memory. Now we have jumping. We want to jump based on conditions. So first, let's think about an unconditional jump. We want to jump no matter what. We have the pop instruction. So this pops whatever's on the stack into ESP. So this is essentially like taking the stack pointer to wherever we want along the stack, and then we return. Question: how can we make an infinite loop using this gadget? Any ideas?
Make the address being popped the same address. Then it'll just keep popping that over and over.
Precisely. Yeah, so I guess that's as straightforward an answer as we can get. So a conditional jump. Now we normally use the compare instruction, but well, the compare instruction does set flags and jumps accordingly. But the difference is that when we use that kind of jump, we change the instruction pointer. Here, we want to change the stack pointer. That's different. Because our instructions are based on what this stack has, because we're obviously going to exploit a buffer overflow. And changing the instruction pointer isn't really helpful to us. We want the instruction pointer to go where we want it to go. So we want to find a way to change the stack pointer. Now, it's a little difficult to go over the exact mechanism in this frame time, but what we can say is that, let's say we get the value we want to evaluate the condition on, we negate it. So when we negate it, every single instruction in x86 sets certain flags, regardless of whether you want it or not. One of them is the control flag. If it is negated, if we have a value of 0, the control flag is again set to 0. The value is set to 0 again because negative 0 is equal to 0, and the control flag is set to on because whenever we have an evaluated expression to 0, the control flag is set. Then we store the control flag into the stack. We have a gadget for that. And then we can store a displacement value where we want, based on the condition, to take the stack pointer to. And we saw how we can do a jump. And then we do Boolean operations on the control flag and do a jump accordingly. One important gadget is that this is a way that we can add the value to the stack pointer based on the displacement value we want. One of the important concepts that I feel was very interesting is that you have these other instructions over here that aren't particularly useful, but they aren't destructive to what we want to achieve. We just want this instruction, and once this value has been used, even though the rest of the instructions in our gadget are kind of modifying this value, because it's been used already, we don't particularly care about it. Right. So now we want to do system calls, function calls, like arbitrary code execution as we do in return-oriented programming. libc has a bunch of system calls which trap the program execution. So when we do any kind of function call, we kind of store that value into registers. The RDI, RSI has parameters, and then further parameters are stored in the stack. We know how to do all of that now. We can pop an instruction, pop a value into the register, and we can store any kind of constant onto the stack. So we know how to do that. So we can do any system calls we want. Now, bringing it all together, this is how we can form a shellcode. essentially we have the bin sh is the name of the program that we want to execute. We use the exec system call, which essentially executes whatever we want. And together, I mean, obviously there's a bunch of complicated systems going on here, but combining these gadgets can help you execute a remote shell on your attacker system, and you have basically anything you want to do based on the permissions of the user. So,
Okay. So basically, now that we've discussed all that, just, potential areas for future work that the paper discussed, well, the first area is greater automation integration with existing technologies. So, currently with the way it stands, we're manually running the Galileo algorithm. So, paper mentioned that it should be possible to analyze these code sequences automatically and discover how to combine them into useful gadgets instead of having to manually run through Galileo by the hand, by just running it manually. And given a collection of gadgets, one could create a return-oriented backend to the DCC or LLVM. And then the other one is attempt to validate or invalidate, we don't know which one it'll be, the thesis by examining the C libraries on other platforms. So in the paper, it only discussed the particular distribution of the new libc, but it's basically we're just combining gadgets and x86 or basically assembly level instructions to create a useful attack sequence. So it should be possible to do them on any other language, universally applicable. So we can validate and invalidate this thesis by checking this on other platforms. And these are some questions, potential discussion questions for you that we thought of when we were reading the paper. One is, can you think of a way to prevent the return to libc attacks? And the second is, how can you perform a remote attack when you don't have access to the executable source code files? So we could, this is just questions that came to our mind when we were reading the paper, and these are our sources. And with that, thank you for your time, and we'll open the floor to any questions you might have.
Thank you. Really good job, guys. Go back to the questions, and anybody has any answers to these?
Paper sheet talks about the way to prevent or form, a way to prevent return to like CX.
Okay, so we can actually wait for paper 2.
Okay.
What do you mean by second question?
basically, if you don't have the access to the remote, to the executable source code, so that means you don't know where the libc is going to be located if you don't have access to that. So how do you still execute it?
Oh. Yeah, but yeah, this kind of like, defeating the ASLR in some sense, right? So
Yeah, so
ASLR,
I was thinking that what you could do is, because you don't know where the attack does depend on where the libc is located, because it's going to be dynamically
Yeah.
attached during the execution. I was thinking that perhaps you could kind of do an iteration over the address and see wherever it succeeds, because you do have unlimited access.
that could be one. Yeah. There are generally ASLR and breaking ASLR. There are lots of interesting attacks trying to break the ASLR, and all of them mainly the idea is that if you can just leak one thing, basically the idea is very simple and very interesting. It's that if this is my memory, if I can, let's say you are in an island and you kind of know where your different things in the island is, but you don't know how it's rotated. So what you can do is that as soon as you find any small things in your island, then you can, since you know the displacement between this and other objects, you can very quickly find everything else, and then you can find easily the entire shape. So I mean, it's a little bit more details than this, but generally, as soon as you find one thing that's kind of reveals its position, everything else can be very easily found. That's generally the idea. So for other people to see what they, that's it. Okay, so who is next? Yeah.
It's a question on that. So if you were to somehow find like a a gadget that equates to push RSP, pushes a stack pointer onto the stack, and you would be able to see what this stack pointer is, right? And therefore, like,
Mhm.
locate your program in memory that way.
Yeah, exactly.
Can I leave the meeting?
Yeah, you should.
Okay, thank you.
Who's next?
I don't think so. You shared it. You shared the things.
I added it as a PDF, should I have put it as a?
Oh, you have it on the folder?
It's in the folder, but it's a PDF because everyone else did it.
Yeah, that should work. Yeah.
Okay.
So before that, let's see if. Freddie, are you there? There's the third presenter.
Yeah, I am.
Okay, so so I sent you a message on campus Fire. Can you check that? Because I think we kind of like running late. And I think the easiest thing for us to do is that if you actually just present it, record it on Zoom, and then we can share it with everybody, that probably save us some time. Because I guess you guys are like 15, 20 minutes.
Yeah, 15
Yeah,
minutes.
probably. Yeah. So we're gonna run short anyway. So let answer my message on campus where we can talk about it. Okay.
All right.
Thank you. All right. Thanks. Yeah, everybody else, please upload your PDF onto that shelf folder. Still 4.2, 4.3, 5.1, and 5.3 is missing, so. I shared the folder on CampusWire for uploading your PDF files. Yeah. Andrew, can you move a little bit so I can see my, oh, okay, thank you. It's this one. Actually, I have to move it here. It's full screen. Sorry about that, guys. It's hard to.
Jim, for whatever you're looking at, make sure it's over 50 megahertz at least.
It is.
Okay.
Yeah, we want to be able to see the clock.
Also,
Okay.
okay. Whatever. If it's $100, get 2 of them.
What?
If it's under $100, get 2 of them.
There's only one less 70, and we're gonna get like 15 or so.
Okay.
No.
There you guys. Sorry about
Alrighty, so the next slide, do we scroll?
that. Just do next on the arrow.
Alrighty. Do you want to be on this? Yeah, sure.
Sean.
Hi, I'm Andrew Fantino, and this is
Prem Girdhar.
and we are presenting on paper 2, jump-oriented programming, a new class of code reuse attacks. So a little background on our problem. Say that I'm a hacker and I want to get onto Professor's machine, but he's a very smart guy and he has some protections that prevent me from returning it too many times on the stack. It automatically checks that. So I can't use the stack in order to try and use stack smashing to attack the professor's machine. Instead, I have to find a new way to execute instructions, execute gadgets to get that shell code that the previous table was talking about. Next slide, please.
You don't have to press down, just press right. arrow,
Oh,
and then,
okay.
yeah.
Sure. All right. So a little bit of background. We've already learned about buffer overflows and all that. Basically, the programmer allocates a buffer, but doesn't like actually limit the input size. So when an attacker overwrites the stuff that's above the buffer, which is the return address, then they're going to be able to basically get the program to run anywhere they want. And suddenly the program is on a string. And we talked about the limitations with that and how it can be solved with like canaries and a lot of other stuff. So instead there's return-oriented programming, which is like, instead of just like a basic buffer overflow, you're not injecting your own code, you're sort of reusing gadgets that exist in a gadget farm, which is, and just like the gadget catalog, also known as a gadget farm, is the set of all the gadgets that are available to use. And we've already talked about all this stuff. So let's get into how do we fix return-oriented programming. We've learned that you can do the like W XOR X thing, which is essentially saying you can either write to the stack or execute from it, but not both at the same time. And as for the return instructions, if there are solutions to like detecting return-oriented programming attacks, which are like if you detect when there's too many return instructions in a small space, which is what this paper does, the Dyn IMA. And then another solution would be, what if we just removed all the return instructions and sort of like modified the like code in a way that doesn't actually use return instructions? That's what this returnless kernels paper talks about. So the question now is like the problem that this paper is trying to address is how can we perform a code reuse attack that avoids these defenses and gets around the sort of like limitations of a return-oriented programming attack? Oh yeah. So of course the threat model in this paper was the same as a return-oriented programming attack. The idea that the attacker can write to a buffer and they can write certain bytes to it, but what they cannot do is modify the code itself, and they can't modify the instructions that are available in the program.
Yes.
So you have to basically like achieve your attack without being able to inject code yourself.
So this paper assumes that on a potential user's machine, there is a user application that is buffer unsafe, which means that if you only install well-coded things, then you are not vulnerable to this threat. However, that's unlikely. So next slide.
All right.
This is good. Yeah, it's me. So now moving on to our contribution for jump-oriented programming. This is where, go ahead. We're going to be talking about our jump-oriented program. So instead of using the stack and a bunch of returns, we're instead going to use indirect jumps. So this is like creating your own computer. So has anyone here taken CSM 152A? Okay, great. So it's like for those of you who took it, it's like creating a data path and control within the code of your program. So instead of using the stack, you're actually using memory and different types of gadgets that jump back into themselves, right? So there's actually 3 types of very important gadgets, and they all fall under these tiers, right? So there's a dispatcher gadget, which essentially acts as a program counter. So this will set number in memory, and that will allow us to step through each of our instructions in our attack code. Then there is the functional gadget, which is the basic gadget, right? That's the gadget that does some sort of operation. So like going back to paper 1, that's the sort of gadgets that they used when you saw on stack. It's the same idea, just it jumps back into the dispatcher gadget. Then there's the initializer gadget, which sets up this dispatch table right here. This dispatch table is very, very important. So it's a section of memory that the dispatcher essentially steps through. And in that section of memory, it has the addresses to functional gadgets. So what will happen is that this dispatch table is essentially all the memory that you need to execute your shellcode. And then your dispatcher is just going to step through that and execute your shellcode as it moves. Next slide, please. So what makes the gadget useful? There's the dispatcher gadgets. The dispatcher gadgets must modify the register that it jumps to, and it must update that target predictably. So, and then your functional gadgets must not modify the dispatcher gadgets register. This is very important. So for CS33, you know that there's like multiple different types of special addresses or special registers, right? If you change your special register that is used as a program counter in your dispatcher gadget, you will actually lose control of your machine. So you actually cannot use that register. So now of your like 16 special registers, you can only use 15. Next slide.
Right, so how was this it's evaluated? Basically, the evaluation method was like determining whether we can find gadgets and execute shellcode. So in order to find a gadget, basically you just like look at the executable portion of the application binary and you look for the 0xFF byte followed by the like values. And from there you move backwards byte by byte until you find like instructions that you can use. And you evaluate each of these gadgets with a heuristic that like basically lets you select the most useful ones. We'll get into more details on all of this soon. So the benchmark for any good program, of course, is being able to execute shellcode. Like if you want to be able to attack the program, you have to be able to open up a shell that lets you do anything you want.
Alrighty, so we did kind of skip over a really big part of the evaluation. Can we go on to the next slide? So part of the evaluation of this paper mentioned that, welcome back. So part of this evaluation of this paper mentioned that they used x86 on a Unix-based machine and they used libc for their they used libc as their code base to calculate their gadgets, right? This is really important because x86 is used on most personal computers nowadays, and it also has a couple quirks that makes it easier to find gadgets. For example, negative numbers in x86 are 0xFF, and then followed by like all of those for small negative numbers. And what's really funny is that 0xFF is also the indirect jump instruction. So that makes it really easy for you to find indirect jumps throughout memory, just looking through the program binary, right? Another quirk about x86 is that it's a variable length instruction set. So that means that only a couple of bytes have different meanings than like the total instruction. So you actually have to evaluate the entire binary to see, oh, these like set of 2 bytes mean something really important that the programmer didn't actually need to do, right? Also, now for libc, this is also very, very important. Libc is something that is a library, and for every dynamically allocated is a library that is dynamically allocated to every program in Unix-based operating system. So this means that if you have any buffer unsafe application, libc can be linked to it, and you could call libc from that buffer unsafe application. This is also nice because libc is huge, because it needs to be, and so that gives us a lot of space to try and find gadgets. Here is an example that Prem will go over for you guys.
Yeah, so this is an example of an instruction that you might find in a gadget farm somewhere, just like some random offset, you add it to a register and then you return. This is like, actually, this is a gadget that I stole from the attack lab in CS33. And basically we can see that it's like a very specific number being like offset being added, and it's kind of not really useful. But if you look at the byte sequence, it looks something like this. And if you just take a smaller like subset of the bytes, starting from this 4.8 and then going up to the return instruction, which is the C3, you find that it actually encodes something different entirely, which is this move Q instruction, moving from one register to another, followed by a no op and then a return. And as you can see, the intended instruction may not be useful to us, but if using like an algorithm to actually like go through and find all the examples of unintended instructions, you can see that some of the instructions available to us might actually be far more useful in terms of like organizing our attack. And the fact that libc has so many like instructions just in general, like so many different libraries and functions and all that, means that there's essentially a massive amount of instructions that we can pick from, both intended and unintended. So what do those numbers actually look like? We see that there's like the algorithm that they used found 31,000 potential gadgets in the C libraries. And this was before filtering it out like with heuristics to find the best ones. And more importantly, they found this sysenter gadget that can make system calls without actually modifying the stack. So that, of course, like achieves the purpose we initially intended, which is to essentially simulate a return-oriented programming attack without modifying the stack. So using the sysenter like gadget, if you can set the registers a certain way, you can actually execute a shellcode without ever pushing anything onto the stack or using the call queue or anything like that. the like actual instructions for that are here, but it's not really important to understand what it's all doing, except that essentially the sys enter allows you to execute shellcode if your registers are set a certain way.
It's
And-
cool and it works.
Indeed. All right, and as for discussion and potential future work, so we looked at this paper and we were thinking like the sort of jump-oriented programming and how it works, because of the fact that you have to essentially like find a dispatcher gadget and then find a way to like consistently and predictably offset your values before you can jump around the program. It's a lot harder to automate a jump-oriented programming attack than it is to automate a return-oriented programming attack, in which you only have to like just push a bunch of addresses onto the stack. So given that, an important question to figure out is how can we more effectively automate the creation of jump-oriented programming attack code? And by automating it, thereby we can figure out a solution to stop it. And secondly, jump instructions are more varied and complex than return instructions, because jump instructions obviously take like value parameters, whereas return instructions are just return to whatever's on the stack. So how can we accurately detect and thwart jump-oriented programming attacks, given that jumps are so much more like varied and can be used in a variety of ways that returns cannot? And jumps are just like common in code control flow in general. So it's like, how can you detect that in a way that like for example, DynIMA did for return instructions? And lastly, there is currently a way to compile without the unintended jumps, which would make the jump-oriented like programming attack infeasible, but it's not widely used because of like massive performance costs and overhead. So another question would be, can we find new ways to get around this?
But wait, there's more. Next slide. This paper was published in 2011, so that's like dinosaur years in technology, right? So actually, there's a couple of new technologies, such as Windows Control Flow Guard, that protects against this by using some like special techniques of stuff that's much more complicated than I can understand, called control flow integrity. Most control flow integrity protects against ROP, and some actually protects against jump-oriented programming attacks. But they do add some overhead to the program. And so Windows Control Flow Guard is actually not on by default on Windows 8.1 and should be put on, should be enabled because this is dangerous. Also, there's a couple of other control flow integrity checkers, such as ARM branch target checking, or ARM, branch target checking, which essentially checks if you are branching to where you say you are in the program code versus in your binary, which is useful, but it does not necessarily protect against unintended jumps that you would get in the x86 architecture.
All right, thank you for listening. Are there any questions?
Yeah, it's great
Yes.
that you actually. Oh,
Well, I do have a question. So, for the instructions that you can parse like several bytes in to completely change the encoding, is that predictable, or is that just kind of like you see what happens?
So the actual algorithm that happens is that you use like a text dump on your application. And so they use text dump on libc essentially. Then they step through each byte in text dump and they say, oh, I found 0xFF. Then they check for the byte after, which should be the either register address or a address that's useful. And then they step byte by byte backwards. So they have, once they find 0xFF and then something that's useful, they take a byte back, they see if that's useful, then they take a byte back and see if that's useful, and they essentially store anything that's useful. They step a total of what they call delta max bytes back. That's essentially saying, oh, I step 16 bytes back, and then whatever is useful in that, I'll store in like a separate place. And then after I store all my like potential gadgets, what they'll do after that is they'll do a heuristic, which will essentially say, okay, I have my dispatcher gadget. Now I have to eliminate everything that changes the dispatcher gadgets register. And it also has like, oh, I need to add something, but I need to add something in this very particular way because if I don't, then it won't work. And they have like different heuristics for each type of instruction.
Yeah, and to answer your point on predictability, it's predictable in that obviously like all these byte sequences that correspond to different instructions has to be consistent and defined somewhere so that the computer can actually understand it. So all that information is like readily available in terms of just knowing what like byte sequence corresponds to a different instruction. So if you can examine the hex code dump of a program, you can actually identify those like different instructions, both intended and unintended yourself.
Yeah, it's basically your x86 ISA, right? So you know, for example, what is add. So you have an opcode for add, you have an opcode for jump, you have an opcode for everything. But x86 particularly is a little bit weird because it's a RISC, it's a CISC, it's not a RISC, which means that it's a complex ISA. So it's not like, you always say, oh, my instructions are 16 bits or my instructions are 32 bits. Some instructions are 1 byte, some instructions are 2 bytes, some instructions are 4 bytes, and so on and so forth. And you assume that, for example, your return instruction is 2 byte, and you say, oh, okay, it's or your jump instruction is 0xFF, and you're done with it. But if you actually add an additional 2 bytes to it, now it becomes a 4-byte instruction, which could be something else. And unfortunately, the chances that you can actually find a useful instruction is so high that, as the previous presenter was saying, that it becomes actually a two-complete machine, that you can basically do anything you want with this, because it's just the number of possibilities is so huge that people can actually did show that you can just basically find whatever instructions that you want, and that's unfortunately very unfortunate because the attackers can do whatever. All right, thank you guys. Great presentation. Yeah, so yeah, just and then the third one, I'll post a video just next with the lectures. Please watch that. And just one final thing to say is generally the idea of these paper presentations was to show you that it's just that there's very interesting arm race between the attacks and defenses, and how the attacker can be very, very smart and sophisticated. They can do all these tricks of return oriented, and jump oriented, and then data only attacks, which is the third paper. And unfortunately, usually the attacks are much more successful than defense. We didn't have paper on CFI, but unfortunately CFI is also not something that can completely eliminate this. So we, at this moment, we are kind of like still need to deal with this type of problems. All right. Have a great day, guys, and see you next week. Thank you. Or on Thursday.